see so many people, local people here involved with the KITP and what's going on. And I'd like to show you some work that started here when I was a postdoc here 10 years ago. Trying to look into this mystery of why the very biggest galaxies and the most massive galaxies aren't forming stars. So when we think of a galaxy, think of something like this, right? You have a disk of gas and stars, millions of stars here, and maybe there's some of these spiral structures, which are waves that are moving through the disk. And, maybe you see it on a T-shirt and it says, okay, you are here, somewhere in the outer part of the structure. But of course, you're not here because this is the Andromeda Galaxy. And it's, millions of light years away. You're actually here. So this is a picture I found online. Somebody had gone up to St. Marcos Pass. I guess his name is Bill Heller. And he took a picture of the Milky Way. This is a galaxy that we live in. And that's downtown Santa Barbara. The lights over here. So pretty neat. It says you could kind of do it yourself if you kind of walk off of the road and take a picture of it. So maybe it's worth trying. And that looks pretty different than the thing I just showed you. And galaxies look pretty different than each other. So here's a gallery of a bunch of nearby galaxies, pictures taken with the Hubble Space Telescope. And you can see some of them look like sort of like Andromeda, so like things with spiral arms and kind of flattened. But they don't all. Some just look very round. And they have a variety of colors, you may notice. Some are very blue and some are yellow. I'll have more to say about that in a little bit. And they look so different from each other and so different from, this, that as recently as 100 years ago, it wasn't even clear that these things had anything to do with where we live. So they weren't referred to as galaxies. They're called spiral nebulae. And it was only worked out, the relationship between these two things, through the work of two people. One of them was Henrietta Leavitt, who worked at Harvard Observatory. And her work concerned a particular type of star called the Cepheid star. So here's a plot of what we call a Hertzsprung-Russell diagram, which shows the luminosity of stars on this axis, and there are many orders of magnitude here. So these stars are 1,000,000 times brighter than the sun. Here's the sun at 1. And then on this axis, you have the temperature of the outside of a star, which is also related to its color. So if you have something really hot, it's shorter wavelength, it's bluer, and these are the red things here. And most of the stars live on what's called the main sequence. So the red ones tend to be very faint, and the blue ones tend to be very bright. And because they're very bright, they use up their fuel in a very short amount of time. So these ones live a few million years. And these ones, the sun has a lifetime about 10 billion years. And these ones, they live the whole age of the universe. And their lifetime's much longer than the current age of the universe. So that's the main sequence. And that'll come back in a second. And she was concerned with stars that are over here. And was this instability strip. And these stars are unusual in that they get brighter and fainter with time. So they pulsate on a span of days. And she was able to measure a bunch of these stars in a neighboring, was a small galaxy that's nearby. It's called the Magellanic Cloud. And they were all at the same distance, and she measured how fast they would pulsate and how luminous they were. And she worked out that there was a very tight relationship between this period over where they got brighter and fainter and how luminous they were. So you could go to say, okay, well, this star gets brighter and fainter over a period of 10 days. Therefore, it's 3,000 times as luminous as the sun. And this now became a wonderful tool. Unfortunately, she died of cancer before she could apply this tool herself. But she knew what she had on her hands. She had a way of finding something that was very bright that you could look for really far away and know how luminous it was. And of course, if you have a light bulb and you know how luminous it is, and I hold it some distance from you and measure how bright it appears to you, well, then you can infer a distance from that. That's something we call a standard candle. And so, in the early 20s, Edwin Hubble here, who was working at Mount Wilson Observatory, which is outside Pasadena. Here's a picture of used this technique to look at a bunch of what they were calling spiral nebulae at the time. So you have to go there night after night after night and look for these variable stars. They get a little brighter and a little fainter, and you have to measure the period of each one. And he did this in dozens of galaxies. And he was able to derive distances, right? And so you were very far from here, right? So he worked out that Andromeda was at distances that were enormous compared to those within our Milky Way. So that's placing these spiral nebulae outside of the Milky Way. And if you relate these distances to their size, he figured out that this distance from here was comparable to the entire size of the Milky Way. And so this is the first time that we knew that we were just in one of millions and billions of galaxies that were all this sort of similar scale to our own. So we did a little more than that. So I showed you that there were a variety of appearances that these galaxies have. And he organized them in this little diagram here. It's called a tuning fork diagram. And so the E stands for elliptical galaxies. Those are those round-looking things that you saw. And then if you kind of march along here, you put more elongated things here. And then you come to spiral galaxies like our own. And he had two types depending on whether there was a bar in the middle. Okay, and he thought this was maybe an evolutionary sequence, like they started out over here and they kind of morphed in over here. But we don't think that anymore. I'll show you what we think in a second. But this classification is sort of important. And it turns out the most massive galaxies are sort of sitting over here on this diagram, even though we're somewhere over here. The other thing you could do is now we have distances, so you can relate those distances to how fast the galaxies were moving. Now, how do you know anything about the motion of a galaxy? Well, he used something called the Doppler effect. So here's a little diagram that I sometimes show when I teach the undergraduate class. You have a little train coming along. And if there's a sound off the front of that train, maybe blows a horn, and the train's coming to you, well then that sound wave is compressed. So you hear it as a higher frequency. And when the train passes by, when you're behind the train, then because it's moving away, that wave is extended, it's stretched out, and you hear it as a lower frequency. You can think of a race car when it's driving by, it goes, a kind of a characteristic sound. That's because sound waves are compressed as they're coming towards you, and they're extended out behind. Right? Now, the same is true of light. Now, the speed of light is much faster than the speed of sound, so you really have to get something moving very quickly to notice that you're compressing now waves of light, or stretching them out if something's moving away. But if you're moving things at speeds comparable to the velocities of galaxies, then what you notice is that the wavelengths of light, say you have 3 colors of light, each corresponding to a different wavelength, and they lie here in the laboratory, and if you move something away from you, well then those wavelengths will be stretched, and they'll shift to redder colors. And if you move it towards you, then those wavelengths will be compressed and move to bluer colors. And that shift is proportional to how fast it's going. So he was able to measure not only how far these things were, but actually a lot of those motions, measurements already existed. But he would be able to put the two together. And the first thing that you notice is that this galaxy, okay, it's 2.5 million light years away, but it's actually headed at us. Okay, so I'll show you most galaxies are not doing this, but Andromeda is actually headed our way. And it'll approach us in a few billion years. And here is a little simulation of what we expect that to be like. There you go. Here we are. There's the Milky Way going around. And here's Andromeda. This is a little galaxy called Triangulum. It's also nearby, and it's headed our way. You can see a timer here. It takes quite a long time. But eventually, they collide. And there you go again. And they form into this roundish galaxy. Hopefully you can see that okay with the lights.
Sure.
But so the shape of this has changed. It's turned into an elliptical instead of a disk. And also, you may have noticed that they started out kind of bluish, and this thing is looking yellow. And the reason is, if you're actively forming a lot of stars, well, then you'll have some of those very short-lived blue stars that I showed you on that HR diagram. But when you stop forming stars, well, those short-lived blue stars go away pretty quickly. And so the color of this collection of stars here is going to change from blue to yellow. So this is a round galaxy. It's a big one. It's not forming stars. And that's sort of typical of ellipticals. So these very massive galaxies stop forming stars. So he now had velocities. You can take the velocities of these various galaxies and put them on a plot here with distance on the x-axis. And here's Andromeda. Okay, it's coming at us. But if we ignore that one, then the general trend is that the further away a galaxy is, the faster it's moving away. And that's referred to as the Hubble expansion today, or Hubble's law. But what it gives us here, so it means that everything is expanding, the universe is expanding. But interestingly, it gives us a way to measure something that we can get pretty easily, the velocity that something's moving away, okay, by taking light and seeing if it's, how fast the wavelengths are stretched to longer wavelengths. And then infer from that the distance. Okay, so you can measure a velocity and infer a distance. So what that looks like is, in the lab you might have these little features here. This is how bright. So if you take all the light from a galaxy and spread it out in wavelengths, this is how bright these different wavelengths appear. And you see, sometimes it gets a little fainter, sometimes it gets a little brighter. And those things are shifted in a way you can easily measure. And now you know the velocity, so you know how far it is. And this is a really great tool because, so this is now a picture of a small patch of the sky taken from the Hubble Space Telescope. And you see that there are thousands of galaxies in this image. And they have various shapes and things. But if I were to ask you, okay, how far away is this one? How would you know? You kind of get the idea that maybe the ones that look bigger are nearer to you than the ones that look smaller. But it's really hard to put a number on that just by looking at these. But now, if you take the light from this galaxy and spread it out in terms of wavelength and measure its velocity, now you can infer a distance. Okay? And this is a really useful thing because distance is equal to time. Right? So light does not move instantaneously from one place to another. Right? So as you see me now, you feel like you see me exactly at this moment, but there's a very, very small but finite delay between light leaving the screen or me to your eyes. If you shouldn't look at the sun, but if you do, you'll see it as it was 8 minutes ago. All right? If the sun were to disappear, it's not going to disappear. You wouldn't know for 8 minutes, right? You'd have no way of knowing. Right? So as you move to cosmic scales, the distances between galaxies, these time delays become enormous. They become millions of years, and even billions of years. And you can actually look at what's further away. Okay, look for the faster moving galaxies that are further away, and infer from that what was going on at earlier times in the universe. So the whole history of the universe is there for you to look at, just by measuring how fast things are moving away, and then using that to tell you what time you're seeing them. So this is a really, really powerful tool that we have. And what do we learn from this? What if we go and we say, okay, well, let's look at these galaxies. Let's compare the universe as it was a long time ago to how it is now. How did things evolve? Okay, well, this is a 5-minute tour of how things evolved. So if we go to very early times, we get something like this. This is an image of the whole sky. It's flattened, like you might flatten an image of the Earth on a map. And what you see is that actually, things were very, very smooth early on. So this is at about 100,000 years after the Big Bang. And there were structures where actually these are magnified by many orders of magnitude, so you can see them with your eyes. These fluctuations are a very small 1 part in 1,000-ish, or smaller. All of this is seen in as microwave wavelengths. So this is happening so early, it's moving so far away that this light is shifted from where you would see with your eyes all the way to the wavelengths that you see that you have in your microwave operating. So we call this microwave background. Okay, that's very early times. Then if we kind of step forward in time, this is when the universe was about 1 billion years old. Now, all that stuff that was relatively smooth starts to lump together. So gravity pulls those lumps together. And you start to see structures forming. And sort of in the intersection of where these structures collect up material, that's where you start getting galaxies. And in general, gravity is really good at pulling things together. So as you march forward in time, you get bigger and bigger structures. So early on, the universe was relatively smooth. There wasn't a lot of structure. And then, as you march forward in time, you see bigger and bigger structures forming. Okay, and that's today. So that's the history that we infer if we kind of go through it. Now, these are plots on giant scales. This is 500 million light years across. And our own galaxy is, let's see, it's about 30 million light years across.
Evan, are those simulations?
Yeah, this is a simulation. It's a pretty good representation of how gas is collected. So now what if we were to say, well, what about our own neighborhood? What about our Milky Way? How does it fit into this? This is how structures are forming on these gigantic scales. Let's just kind of zoom in and see how our Milky Way may have formed. So here's a visualization of the simulation of the history of how the Milky Way may have formed. And it's showing how the gas collects over time. So you see gas coming along these streamers, and there's this spinning disk up here. It starts to move down, and now you'll see another disk merge with it for a second. And then it grows the disk again. Right? So galaxies grew over time, larger and larger, by accreting material, from this medium that surrounds all galaxies. But they also merge together over time. And those processes kind of happen together. But then you might ask, wait a second. This is a disk galaxy. It's supposed to be the Milky Way. It looks like a nice disk. But I saw that thing merge, and the first time that you showed me something merging, it turned big and round. What happened there? So it's kind of... So there's a classic answer to that, and it has to do with cooling. Okay, so if you bring a lot of material together through gravity, well then you're going to condense it, which is good if you want to make stars, but you're going to do something else. You're going to heat it up, because a lot of energy is released whenever you use gravity to pull something down. If you put something on the top of the hill, you roll it down the hill, it's going to be going pretty fast when you hit the bottom. All right, so you can imagine this is sort of a cartoon. Now, you saw how the gas was coming in at different angles and stuff, but this is a very sort of smooth version of that. And now, gravity is going to come in and make it more compact, but it's also going to heat it up. It's going to be hot, and it won't initially be able to condense to the point that it can form stars. And it would stay that way, except for it's able to radiate that heat over time. So light leaves it, carrying energy, and that cools it over time. Right, so if you wait a little bit, then light will carry this energy away, and then this hot thing will cool and condense, and you'll form, a disk like this. And that's a great place to form stars. All right? So the classic story of why big mergers today lead to big round things that are not forming stars, and why these smaller mergers back then lead to more quiescent things that keep their disk structure and form stars has to do with that cooling. The bigger the structure you're trying to assemble, the more you're going to heat it up, and you're just going to have to wait longer to cool. So two tiny little galaxies merging together won't heat up much. They could form a disk again pretty quickly. But if you take two big ones, well, then you're going to be in trouble. It's going to take quite a long time for them to make stars again. And so that was a story for a really long time, from when I was young. But more recently, when people, and this works out on paper, but more recently people have been able to do simulations of the type that I've shown you. So not only sort of estimate these things, but do very accurate reconstructions of how this may have formed. And they found that this actually doesn't work at all. It sounds like a nice story, but it gives you gigantic galaxies forming stars 10 times bigger than anything that we see. But there's an even more fundamental problem with this. Okay? And that's represented by this plot, which can be a little bit confusing. Let me walk you through this plot. So what's shown on the x-axis is time. Okay, so as you go from this side to this side, you're moving from early times in the universe to today. Okay? And redshift goes this way. These things are moving away more quickly. So that's earlier in time. And on this axis, also in funny, strange units, is how luminous galaxies are. So the more you go up here, the bigger they are, the more stars they are, and the brighter they are. And this shows you, as a function of cosmic time now, what is the typical luminosity, the number of stars, of a galaxy that is actively forming stars. Okay, so it was high back here, and then it steadily dropped with time. Well, that's backwards, right? So if all you have to do to make a really, really gigantic galaxy is wait for that thing to cool down, well then if we wait all the way till today, well we ought to be able to put together a super gigantic galaxy, right? It should be no problem. But in fact, the universe seemed to be really good at making big galaxies early on, and now it can't really do that. For some reason, it doesn't know how to do that anymore. And that's really very strange. And that's where things sort of stood about 10 years ago, I'd say. So there's something missing from this picture. There's something that needs to be included to make sense of this trend that we see. And what that is black holes. Okay? So in the center of every galaxy is a black hole. Okay, and they're much more massive than the ones that were detected at LIGO that were a few times the mass of the sun. These ones are what we call supermassive black holes. They can be millions up to even a billion times the mass of the sun. Okay, and of course, nothing can escape the black hole itself. Right? So if you fall into a black hole, that's very bad. Never going to get out of there. But you can get pretty close and still sort of escape. So this is an artist's rendition, of course, of a black hole that is in the midst of growing. It has this accretion disk around it of gas and material that is slowly spiraling around and making its way down. But not all of it makes its way down onto this black hole. A lot of it actually shoots out in the form of a jet. So it gets thrown around faster and faster, and some of it ends up in a jet. This is a real picture, not an artist's rendition. There's a whole galaxy right down here, and these are enormous jets. The scale here is 80,000 light years from here to here. So light takes that long to get from this point on the plot to this one. And you see these giant jets of material coming out from this galaxy that has a black hole down at its core that's forming. I thought this was appropriate for this event. Someone once told me that if you want to think of sort of the geometry of what's going on here, you can think of this wine aerator, right? So like, here's a jet of, delicious wine as opposed to like high energy particles dropping into your cup, and air is coming in like along this way. Right? And this is the same geometry you would have here. There's a disk down here. Stuff is coming this way, but it's also shooting out. So when I was a postdoc here at Santa Barbara with professor over in the physics department, Peng Oh, we proposed, well, what if you include these forming black holes into the sort of story of galaxy formation? So then you might put together a galaxy like this. Everything's fine and happy, and it's going to form stars, but there's that black hole that we neglected, and when that forms, then it could do a lot of damage. It'll shoot these jets out, and they have the potential to heat a lot of material around it. So what if we were to include this process of heating associated with when black holes are growing into the history of galaxy formation? How would that change the trends that you see? So here is a little movie from a computer simulation that we did of this. Oh, so let me tell you what you're looking at before it starts. I think it starts automatically. Well, I'll let it loop. So this is a big, big region now, much bigger than a galaxy. Galaxies are little tiny things here. And what you see is the amount of energy. Well, so it's essentially a plot of pressure, actually. So it's the density of gas times how hot it is. And you can see that where galaxies form along these sort of knots of this gas that's collecting together, you see these outbursts. Some of them are really big. I think this one has a nice big one. You see? They're heating up their environment over time. And from this, we're able to infer, if you include this process, what kind of galaxies should be forming stars over time. Okay? And it looks like this. So early on, you're building up bigger and bigger galaxies because your gravity is just collecting stuff together. Okay? And yeah, black holes are growing, but they're all kind of small, and they don't do that much damage. But when you come to late times, now you're putting together really gigantic black holes, and they have a lot of damage. They heat their material around it a lot. And they make it impossible for this stuff to collect back together and form more stars. And so this reversal occurs, and you have this trend going down here. So we wrote that paper in 2004, and other people started thinking along similar lines, and this is the number of papers that refer to black holes and feedback since then. Now it's a whole big thing. There's conferences. Where are these conferences? I don't even know. Santa Cruz, Shanghai, wherever, all over the world. People talking about this. And in fact, it must have to be, right? Because it's on the Discovery Channel. Right, so here's this jet, and all of a sudden look at that, it pushes it out of the way. I couldn't get the audio to work. There's a voice that says, black hole destroyed. So this all kind of works, and it's popular, but is this even true? This is supposed to be science, so you shouldn't just come up with a story that explains what you know, right? You try to make a prediction of what you can measure to check that you're actually right. And that's the last thing I want to talk to you about. And we can have some questions after that. So how can we test if this is right? Well, it makes these nice trends that we like, but if black holes are really heating their environment to the point that the gas can't collect back together and cool, then you ought to have a lot of hot gas lying around. You can't really avoid that because this is the gas that would have made stars. You're making it really hot. And there's this, if you have a lot of hot gas and you have a light source of some kind behind it. Now, as you may have heard, light is a wave, but it's also a particle. And these particles of light, we call it photons. And if one of these particles of light hits one of the electrons in this gas, so there's particles zimming around in the gas, and sometimes they hit the light, it will leave this collision with a little bit more energy than it went into this collision. So you have to see this thing coming along slowly, and this electron just smacks into it and it comes across at a faster velocity. Right? So you have a light source and something hot in between, and it shifts the light. Okay, well, Okay, how can we do? Well, so how is that related to what I'm talking about? Well, we actually have a light source that comes all the way to us from the early universe. Right? It's that microwave background that I showed you. That light that's been shifted all the way from where we see it to our eyes to the wavelengths that you might see. Well, you won't see, but you shouldn't look in a microwave oven. But anyway, the wavelengths that are in a microwave oven, right? So that's a light source. And if we put these clouds of hot gas in front of it, right, then we will take some of this stuff and shift it to higher wavelengths. Let me show you what that looks like on a plot like this. All right, so what is this a plot of? So this is, imagine you take the light from the microwave background and you spread it out as a function of wavelength. Okay, so what you have here is wavelengths. These are really long wavelengths, and here you have short wavelengths. Okay? Then, if this light moves to you through some hot gas, then these longer wavelengths here are going to be shifted up over here. There's going to be a shift. This particle of light here is going to bang into an electron. It's going to be shifted over to here. Right? And this overall shift turns out to depend directly on how much hot gas you have between you and this light source. All right? And in fact, in these funny units, we can make a prediction of how much this should shift if the only thing heating that gas was gravity. And then if we go out and measure that shift, and it's bigger than this, well, then something else must be contributing too. All right? So we have something we can measure. It's this shift. That you don't have to worry about these funny units, but you know what it should be. And we can measure what it is and see if there's this excess that we would expect. All right, so how do we do that? So we work with data from a variety of telescopes. So what you do is you essentially have to do a survey of what's going on around the biggest galaxies. So what does that mean? So we had to find a whole bunch of big galaxies, thousands of them. Okay, and we did that with these two telescopes, the VLT in Chile and Blanco telescope in Chile. We used them to find thousands of these galaxies. And then for each one, you can look around it and say, how much hot gas is around it? How much do I see that shift occurring? And you can compute an average shift for all those 1,000, right? It's kind of like doing a survey. You could say, okay, well, let's find 3,000 of a certain kind of people and ask them how much hot gas is around where you live. Right? And then and you can make an average of that. Right? So for each of these, okay, so for each time you have a galaxy, you can look at, we use this telescope here, the South Pole telescope, and looked to measure the microwave background around that little patch of the sky. And then we did an average. All right, and let me show you a picture of that average. All right, so what this is for every single galaxy, there is some kind of, this is the amount of light that reaches you at a wavelength that's about over here. Okay, 140 gigahertz right here. Okay, so if there is a lot of hot gas between the microwave background and us, then there ought to be a hole here. It's not that there's extra emission, there's actually less, right? Because it's shifted over here. Okay? And we have an expectation of what that shift should be in the absence of this extra heating mechanism. And here's our measurement. Right? So it's about twice that, but it's still sort of uncertain. Right? So it's looking like there might be something to what we're saying. But that's the best measurement we have so far, so I can't tell you definitively. But I believe that within the near future, I can tell you that when we merge with Andromeda or not, there may or may not be a quasar or this active black hole that blows out gas to the point where it can't bloom. And, I don't know. I'm happy to.
Questions?
I wanted to go back to you showed the picture of the microwave background, and then after that a couple of simulations like 1 billion years after current day. My question is, is there, or can you make an experimental version of that? You were saying that the wavelengths from the shortly after the Big Bang were shifted to the microwave. So if you collected images of the universe at microwave and then progressively longer, shorter wavelengths, would that be simulated?
Well, sort of. So that's a good question, right? So it's a simulation, so you get to see everything, right? So we can compare it to this, I guess. All right, so here you have a bunch of galaxies, and the faster, further away moving ones tend to be the redder ones, okay, because all their wavelengths are shifted to be longer. So when you do this kind of measuring, well, what redshift are you at? Then it is true that as you get redder and redder, you're talking about earlier things. And you can place them and relate that to what you see in this kind of a movie. And these galaxies they occur at the little nodes here. So this is a picture of all the gas, that most of which is invisible to us. But then the galaxies form kind of on these intersection points, and they make stars, and that's something we can see. So we have to relate this to what we see. We have to just sort of look at where the galaxies are.
I guess what I'm asking is, so the previous image was microwave.
Yeah.
Is there an equivalent wavelength 1 billion years ago that would reproduce this type of map?
Yeah, no. You can't do that, unfortunately. Yeah.
Why can you do it for microwaves just after the Big Bang?
Oh, that's a good question. Why not?
Why can't you do it?
Well, it's much fainter. Why is it much fainter? I think it's because of the overall expansion, right?
Well, he's asking it one. You're asking it 1 year.
No, I'm asking
1 year.
You're asking so here you come, 100,000 years later, and you come 1 billion years later. Why is the gas suddenly invisible now? Well, it's much lower density. I think that's the key.
Sorry. So this is an image of the microwave background.
Right. This is actual experimental.
This is a real image of the microwave background, right? So this is real, and then I think your question is, well, why can't we just do this again later on? Right? And the reason you can't do that here is I think it's because the density is so low that any kind of mission becomes impossible to see. Right? So the universe is getting less dense with time. And by the time these stars arise, you can't see it. But that being said, people are looking for a neutral gas that's a little bit earlier times than this, that does emit to the point where it should be detectable. It would be observable in the far radio, and that's a difficult place to look because cell phones and everything else. And the atmosphere is not so good. But there is a signal a little bit earlier than this that is detectable. And it occurs in the radio. It has to do with the spin flip transition, the one that's used in MRI. So people are trying to do that. But by the time you have galaxies sort of everywhere, it's really very, very difficult to detect this gas.
You can maybe say a little bit about what's the contrast between the densest and the least dense regions at 1 billion years compared to what it was.
Oh yeah, so So this contrast is these are 100 or 1,000 even, right? So these are very, very, and this is 1 over 1,000.
Right.
So these are very, very small. But this thing is really bright and everywhere, right? It's easy to see. This is not.
You didn't mention dark matter in your discussion.
That's true.
I guess because it doesn't enter into your story, but presumably it's in all your simulations and in some way. And
Let's see if I have the slide.
And there's a halo of dark matter around every one of these galaxies you're talking about. Does it
Yeah,
Does the
you're
evolution
right.
of dark matter over time change? Like the
I lost my pie chart with the dark matter. So I cheated a little bit. Right, so there, well, I don't know, I don't have a plot. But so there is right. So actually, most of the mass of the universe isn't even gas. I kind of went through that point kind of quickly. It's about 6-to-1 ratio. We have this stuff called dark matter, and nobody knows exactly what it is. But it seems to behave in a pretty simple way. It seems to behave gravitationally the same way that gas does, and planets do, and stars do, and everything else. It just doesn't seem to feel any pressure. So when this stuff is collecting together, as you saw in the movie, the gas and the dark matter, they're just doing it together because everybody's feeling gravity, and nobody has pressure to the point that they can oppose gravity. When the galaxy actually goes to form, right, the dark matter is kind of hanging out on a bigger scale. So say around this guy, you would think there's some lump of dark matter that's bigger. We call it like a halo, because that stuff wasn't able to cool down and condense. It doesn't feel pressure either. So when you get down to very high densities, they kind of do behave differently. But the reason I didn't sort of highlight it in this story is because in terms of their overall formation, when gravity's driving it, they're very much the same. And we know that from a variety of ways you can measure it. I can talk about them.
So when you say that they don't feel pressure, you mean the density of dark matter is basically constant throughout this?
No, so dark matter will feel gravity, so it'll pull together, but it doesn't ever feel pressure. The particles never collide with each other. It never sort of pushes back against.
I see. The density changes, but
yeah,
I see.
Yeah, and the other thing it can't do is, so you think, okay, well, it can't push back, so that means that it's going to collapse more, but actually that's not the case because you can't kind of condense it and then cool it down over time. It has no way to cool down. It's just like a bunch of rocks like flying around. It behaves very much like the stars do, actually. So the stars kind of pass each other and go through. And it seems to behave a similar way.
So Evan, we're spending a few $1 billion for the James Webb.
You want me to justify that? With this mic on?
It's your dollars too.
All right, yeah.
For this story you're telling, what are you most eager to see in terms of new data?
Oh, what would be?
For the galaxy formation, how
For
galaxies
JWST.
form. What's going to be the headline? Everybody here is now accustomed to science breakthroughs, LIGO.
Yeah. That's a very.
I just talked about.
Well, it's going to tell us a lot about early galaxy formation, right?
What do you mean by early relative?
So, before this 1 billion.
Okay.
Right. So, I mean, they're very focused on very long wavelengths, right, and very faint things. So, it's going to, fill in much more pieces of that story when they're merging together at early times and how they grew, and how the types of stars evolved over time. And there's clearly going to be a lot of information of that kind. In terms of like large galaxies later on, it would help to have a larger sample, I think. So the telescopes we have now, but I don't know that it's going to be that focused on the stuff that I highlighted in this talk. I think it's much more focused on earlier processes than anything.
Great.
I have another question.
Yes.
Do we have anything to worry about in 8 billion years when the...
Oh, that's a very good question. You think, oh gosh, it's the apocalypse.
It looked pretty
Well,
bad.
the sun will be gone. Okay, so but set that aside. So let's say we found another sun and everything's fine. Then we're kind of okay, actually. So it looks terrible. Let me show it again. Impending doom of Andromeda coming at us. But actually, the distances between stars are very, very large. Right? So I do this when I teach like the undergrad class. I lay out the planets on sort of the scale of this room. Let's say like Mercury was here, and then Jupiter was here, and then I ask people, well, how far to the nearest star? And the answer is like Mexico City or something like that. So the stars essentially are just going to move right past each other. and not very few will collide or even get close enough to disrupt.
But the night sky would look different.
The night sky would look very different. It would look all like yellow stars and red. There wouldn't be no blue stars to see.
How many stars will get ejected from the galaxy that results altogether?
Oh, that's a very good question. Yeah, you can see that a little bit. That kind of is related to the dark matter. So not all that many. And the reason is because they come with these big blobs of dark matter that's kind of bigger on the scale where you see the galaxy. So maybe when they merge together, you might see something like that. Right? You'll notice a lot of stuff gets flung out like that. Yeah, like way out here. And maybe a little bit is lost, but not all that much, because even when you get way out there, you still have that kind of big dark matter. We call it a halo, hanging around, and that acts to pull you back. But if that wasn't there, it really would be a lot. So that's a good question.
Can you go to the artist's conception of the black holes with the black hole with the jets?
Oh, yeah.
What I was going to ask you is...
I think I just have to flip through. Yes? Go you.
As a scientist, when you look at the artist's conception, what has the artist got right and what do you think the artist has got wrong?
Well, the colors are just kind of arbitrary, right? I think. And this jet doesn't seem to have, it arises from this disk, but here it's just kind of like out there. So, and, the black hole isn't just this like marble-looking thing. It looks like the movie Interstellar, was pretty much right. And so, you see the backside of it and stuff. So the black hole wouldn't look like this marble, and this would have very much more connected with the disk. And then, I don't know what that is. But, the geometry's okay. It's not a terrible picture.
Great. Thank you, Evan.
Okay.
Thank you.